So we have arrived to the dispersion relations in the cylindrical column. This is the result that we had from the previous video. As we know that if omega is positive, then we have two real numbers. Then it will be just stable. If we have a omega is negative, then we have a plus minus I gamma. One is stable, one is damping, another is growing. So we want it to be positive, want omega to be positive. So any term here become a positive term will be considered a stabilizing term. On the other hand, if it's a negative, then it will become destabilizing term. So if you look at the modified Bessel function, Im and Km, you'll find out that Im and Km are always positive, and the Im prime is always positive, Km prime is always negative. So this term is always positive. So those two terms will end up become a stabilizing term. And this term will be always negative, so it will become a destabilizing term. So let's study, based on this dispersion relationship, let's study two specific cases with a certain approximation. So let's first study Bz equals 0, m equals 0. As you can see, Bz equals 0, m equals 0, then this whole term will be gone. So we'll make our life much easier on studying it. So basically this term plus this term is greater than 0, greater or equals to 0. So after some algebra, we arrive to this. Basically, this cancels out, and this goes to the denominator, and we have this expression, and we apply to the boundary conditions of the pressure balance and define the toroidal beta as such. And after some algebra, substitute this in terms of beta. Then we have this beta p less or equals to 1 minus I0 prime over Ka I0. So if we plot this curve, this 1 minus I0 prime over Ka I0, the curve is the red curve. It start at 1/2 and converge at Ka to infinity. So basically anything above the curve is unstable. Anything below the curve is stable. So as you can see, it has a limit of like when of a beta p will be stable or unstable. So the second scenario, we are studying the basically m greater than 0. So it's 1, 2, 3, 4, 5, and Ka much less than 1. So for Ka much less than 1, then the Im and Km can have such approximation, which can be applied to the dispersion relations and arrive to this expression. So this whole thing will be vastly simplified if you look at this to the derivative. Derivative of that divided by this, and this divided by its derivative. As you can see, it will make your life much simpler if you do the algebra, which is trivial. So from here you will arrive to this expression, and with the definition of beta t, toroidal beta, you will have this expression. Basically, you can think the right hand side is a second order polynomial, right? For in the terms of k, so k squared, and k. There's definitely k. So it becomes a second order polynomial. Second order polynomial is really easy to study by looking at the minimum of omega, because this polynomial is definitely like this, and we find out that the polynomial's minimum is this, and if we apply the condition of b theta over bz is much less than 1, and beta t is much less than 1, so those two terms are gone, pretty much. So as you can, then you can find that the when m equals to 0, 1, or 2, so m equals to 0, then this will become -2, and m equals to 1, this will become -1. M equals 2, then this thing will become 0. And the denominator is always positive based on the previous based on the argument of those two arguments. So this denominator is approximately 2. So based on the argument here, then we find out there's only possible to be unstable for m equals to 0, 1, and 2, because this will become negative for m equals to 0, 1, and 2. Where so let's study when m equals 1. If we do the similar algebra in terms of boundary condition of a pressure balance, we'll have this. We go from this expression to here. Basically, you just expand this and substitute some part with this pressure balance and the beta t, and we assume that b theta over bz is much less than 1, so this term will become a higher order term compared to this. Then if we wanted beta greater than 0 to be greater or equal to 0 to be stable, then we have basically this thing greater or equal to 0. So we have beta t less or equal to 2, 1 plus beta theta, b theta over bz ka. So if we assume that beta t is almost 0, then we can substitute beta t with 0 here. Then we left with 0 less or equal to 1 plus b theta over bz ka. And let's assume the b theta over bz could change sign, so then this could be a negative, this term could be negative, so we will make the argument that then after some algebra we'll left with b theta over bz less or equal to ka, and we can impose a more strict restriction, because at first we know that the k is greater than or equal to 2 pi over L. You can consider in this case the L is the length of the column, and if you take the column and bend it and let those two ends connect, then it become a torus, and 2 pi r naught is the major radius, is the length of the column. Then it will go like this. So we need at least one wavelength in this column. So this is the argument. Pretty much there's more than one wavelength. More than one wavelength in the length of the column, and then this become a more strict condition than this based on the algebra. And we know one of the way to define the safety factor is a over a r naught, and multiply bz over b theta. A is minor radius for the context of torus, and r naught is a major radius. If I apply to this inequality here, then we will arrive to basically q greater or equal to 1. I apologize, there's this here. And that is Kruskal-Shafranov Stability criterion. And you can read this in more detail of section 4.5 of the physics of plasma.